Welcome friends. In this session we are going to discuss the baseband transmission of binary data. Since we know that in baseband transmission there is no requirement of carrier signal for transmission purpose, and here the channel is called a low pass channel. So in baseband transmission of binary data, a discrete pulse amplitude modulation is the most suitable technique. This technique is most efficient in terms of power and bandwidth usage. In this method, the amplitude of the transmitted pulse signal is varied in discrete form in accordance with the given digital data. The typical block diagram of binary baseband transmission system is shown in figure. It consists of blocks such as information source, followed by line encoder having clock pulse, then transmit filter having transfer function GF, and then channel HF. After transmitting through the channel, the binary data is received by receive filter, that is QF, and it is a type of optimum match filter. The output of the receive filter gets sampled at t equals to ITB, where t suffix b is the bit duration. After sampling, the sampled output, that is y function of ITB, is passed through the decision making device. This decision making device having a threshold value. The function of the decision making device is to decide or guess whether the output is symbol 1 or symbol 0, that is called binary output data. In this system, the blocks such as source, line encoder and transmit filter GF correspond to the transmitter part, and receive filter QF, sampler and decision making device shows the receiver part. Now we discuss this baseband binary transmission system in brief. Initially, the source generates input binary data sequence B suffix k. At the sampling instant, t equals to k tb, where tb is the bit duration, and k is an integer having value 0, plus minus 1, plus minus 2, etc. The element bk represent binary symbol 1 or 0. This input binary data bk is applied to the line encoder that operates with the clock pulse and produce a level encoded signal that is based on the line encoding. Here, for example, non-return to 0. The encoded output a suffix k having positive and negative amplitude levels, that is plus 1 if the input bk is symbol 1 and minus 1 if the input bk is symbol 0. This level encoded signal is represented in terms of positive and negative pulses of fixed amplitude but having short duration, and these pulses correspond to a unit impulse of opposite polarity. Now, this encoded signal a suffix k act as a modulating signal and applied to the transmit filter of transfer function g function of f, that is in frequency domain. The transmit filter GF produce a discrete pulse amplitude modulated signal that is the basic form of baseband transmission in the form of sequence of pulses. The discrete PAM signal is represented by ST, that is equals to summation AKG function of t minus k tb, where ak is the coefficient and the pulse gt is shifted according to the sampling instant k into tb. Here tb is the bit duration. This discrete PAM signal denoted by ST is transmitted using a linear channel having transfer function HF. At the output of the channel, we get signal xt, that is equals to the convolution of input signal st and the transfer function ht of the linear channel, and it is in time domain. Now at the receiver side there is a filter called receive filter having transfer function qf, and the output of the receive filter yt is again the convolution of xt and qt, that is in time domain. So here we see that during baseband transmission there is a double convolution, one at the channel output and the other at the receiver output, and accordingly we can represent the typical block diagram into the simplified form. Here the overall system indicating transmitter, channel and receiver is characterized by pulse spectrum mu p function of f, that is in frequency domain. In time domain it is represented by mu into pt, that is called scaled pulse. Here mu is the scaling factor. So mu times the pulse pt is equals to gt convolution ht convolution qt. The overall pulse spectrum having input a suffix k, which is called level encoded signal. Here the impulse response pt is different from gt, where gt is the impulse response of the transmit filter and pt is the overall impulse response. Now the output yt of the overall system is sampled at the sampling instant t equals to itb, and we get sampled output y function of itb. And in order to recover original modulating signal a suffix k, that is called the reconstructed version of ak, a decision making device is used. This decision making device having a threshold value lambda. If the input sampled y is greater than lambda, then symbol 1 is selected at the output. Also, when input y is less than or equals to lambda, then symbol 0 is selected, and accordingly we get the reconstructed binary sequence a suffix k. Here we note a point. The pulse pt of the overall system is normalized by setting p function of 0 equals to 1. After discussing the binary baseband transmission system, we move to the major problem in this technique, that is called inter-symbol interference or ISI. ISI or inter-symbol interference is due to the dispersive nature of the low-pass channel, that is called baseband channel. Here the frequency response of the low-pass channel is deviate from the ideal low-pass filter and introduces an interference that is called ISI. Also, here we discuss the effect of additive channel noise. The block diagram of simplified baseband transmission system is shown in figure. The characteristic of the overall system is represented by the scaled pulse spectrum denoted by mu into pf. In time domain, it is given by mu into pt, that is equals to gt convolution ht convolution qt. Here the input signal xt is the combination of line encoded signal a suffix k and the Gaussian white additive noise denoted by wt. So this simplified baseband transmission system produces a modified PAM signal denoted by y function of t, and it is equals to mu summation ak into p function of t minus ktb plus nt, taking limit k equals to minus infinity to infinity. Here nt is called filtered noise. Now the output yt, that is called modified PAM signal, is sampled at t equals to itb. and we get a sampled signal y function of ITB, that is equals to mu summation a suffix k into p I minus k into tb plus n function of ITB. Here we simply put t equals to ITB in modified PAM signal. So from the first term, we separate the summation for k equals to I and k is not equals to I. When k equals to I, we get mu a suffix I into p function 0. And when k is not equals to I, we get mu summation ak into p I minus k into tb. Also, there is a sampled noise, and we assume that pulse pt is normalized. So we put p0 equals to 1. So the sampled output, that is denoted by y suffix I, that is a short form representation, and it is equals to mu into ai plus mu summation ak into p I minus k into tb plus n suffix I. Here the first term, that is mu into ai, represent the contribution of ith transmitted bit, and the second term represent the residual effect of all other transmitted bit, that is k not equals to I, and this residual effect is called inter-symbol interference, and the third term represents sampled noise. So in the baseband transmission of binary data, there is a problem due to inter-symbol interference and channel noise, that is represented by second term and third term. And under ideal condition, that is in the absence of inter-symbol interference and channel noise, the sampled output y suffix I is equals to mu times of ai. And this relation shows that ith transmitted bit is decoded correctly. So in the absence of inter-symbol interference and channel noise, we get transmitted bit in the form of 0 and 1. After this, a decision making device having threshold lambda make a decision and say 1 if input yi is greater than lambda, and say 0 if yi is less than or equals to lambda.